In this video, we'll show you how to deprotect a silyl ether, revealing the alcohol once again. This again can be seen in pretty much any silyl ether that you use. The most common way, and again, there's lots of different ways to protect and to deprotect under different various conditions, but this is probably the most commonly used. What you need in this case is fluoride. We're actually just going to do SN2 chemistry again, but backwards. This is not to say that it's a reversible reaction when you're making the silyl ether. You do need a completely different set of conditions to take the silyl ether off and reveal the alcohol again. And the reason why you need something different is because silicon-oxygen bonds are very strong. These are strong bonds. We're going to see this play a role in other chemistry we're going to look at. Think about microsystems and microchips, and when engineers are working in the clean room and they need things to be really pristine clean and they're working on the surface of silicon. One of the things that they use that's highly, highly, highly dangerous is the fluoride baths. And why they're doing this is because silicon, just with the oxygen in the air, will oxidize the layer of the silicon surface. So you'll have, if this is all silicon, right, that's your silicon surface. It forms bonds with oxygen, right? So this is your silicon. And so you want to cleave these bonds with oxygen in order to do chemistry on the surface of the silicon wafers. How do you do that? Well, they actually run them through these fluoride baths. The reason being is because fluoride forms much stronger thermodynamic bonds with silicon, and it overrides its bond with the oxygen. So you have to thermodynamically entice the silicon away to go in the other direction. So you've got to introduce fluoride. So it's not, the prettiest of reactions to deal with in a lab, because you have to deal with fluoride. Fluoride ions can be very dangerous to work with. You can use TBAF, which is a salt. It comes as a solution, or you can actually just use HF, which is what a lot of the chemical engineers and microsystem engineers use. HF baths, highly dangerous. Why? Because if you get it into yourself, the fluorine exchanges in your body and leaches calcium from your bones, and you could die. So people don't like working with fluorine. Fluorine has its own chemistry. It's so highly electronegative that it behaves almost like in its own way, apart from chlorine, bromine, and iodine in the ways that we've seen it. When we were talking about leaving group chemistry, you never really saw me use fluorine as a leaving group, right? And that's because it's so electronegative, it almost has its own properties. It certainly has its own journals. Okay, so we've got to entice the silicon away from the oxygen, and we're going to do that using a fluoride ion. So TBAF. TBAF stands for tetra, butyl, ammonium, fluoride. TBAF. And it's just a salt that comes in a solution with your F- nucleophile. Now the fluorine simply finds its way to the silicon, and the silicon exchanges the stronger bond, revealing your O-, and then you work it up under acidic conditions to reprotonate and reveal your alcohol. Easy peasy. This one's pretty straightforward. You just had to understand that the reason this happens is because of a more thermodynamic bond exchange.